Problem 39, question B, C and D from chapter 20. So this video is the continuation of the previous video. I will give the link for the previous video in the description. So kindly see the previous video, and after that please see this continuation. So in the previous video I solved the question number A, and here we are going to use the answer of the question number A for getting the answer for part B, C and D. So please kindly see the previous video. That is very, very important. Okay. So in this video, I'm going to find the answer for part B, C and D. So we are going to calculate the entropy change of aluminum, water and the whole system. That means the mixture of aluminum and water system. So in the previous video, we find the thermal equilibrium. That means the equilibrium temperature TF value for both aluminum and water as 343.6 Kelvin. So this answer we got in part A. So what is this TF? So once you mix the aluminum with water, so initially the aluminum will have 100 degrees Celsius. When you mix this aluminum with water, water will have 20 degrees Celsius. When you mix aluminum with water, what will happen? The heat will flow from hot region to the cold region. That means the aluminum is going to lose the heat energy, the water is going to gain the heat energy. But after sometimes what will happen? The thermally equilibrium state will attain for both material. So that means the final temperature, this 343.6, is for both aluminum and water. So we are going to use this value here. So now I'm going to solve the big part question. So here we are going to find the entropy changes for aluminum. That means the entropy change is denoted with the letter delta S. S stands for entropy. So we are going to find the entropy change for aluminum. And for this, we are going to use the formula, the integration of dq over T. This is the formula, where dq is nothing but the amount of heat energy absorbed. So mc dt. So this is the formula. I'm going to use this formula here for aluminum. So when you substitute, and also the most important thing here, when you use this equation, we need the initial temperature of the aluminum also. What is the initial temperature of the aluminum? The initial temperature of the aluminum is mentioned here as 100 degrees Celsius. We have to convert this in terms of Kelvin. So when you add 273, we will get the initial temperature of the aluminum as 373 Kelvin. Now we have to apply the lower limit and the upper limit. The lower limit is the initial temperature of the aluminum, and the upper limit is the final temperature of the aluminum. And here I'm going to take this formula and substitute in this equation. When you substitute, you will get the equation in terms of aluminum as integration of the initial temperature of the aluminum and the final temperature of the aluminum, which is the upper limit and the lower limit. And in place of dq, I have to use this m of aluminum, that means the mass of the aluminum, the specific heat capacity of the aluminum, and the change in temperature divided by temperature, because we have the temperature in the denominator. Now I'm going to move the common terms outside, which is a constant. So mass and specific heat capacity value, I can take it outside. So by that, mass of the aluminum and the specific heat capacity of the aluminum will take it out. So integration of T initial of aluminum and T final of aluminum, which is an upper and lower limit, and inside this integration we will get dt over T. And in mathematics, in calculus, you studied the concept of integration. So integration of dt over T gives the value of natural log of T, right? So mass of the aluminum multiplied by specific heat of aluminum, when you just take the integration, this will change as natural log of, and when you apply this initial the upper limit and the lower limit inside, you will get T final of aluminum over T initial of aluminum. Now I'm going to substitute the value, the mass of the aluminum, which is already given in the question. So mass of the aluminum, they mentioned here as 400 gram, so 0.4 kilogram. I convert the gram to kilogram, and the specific heat capacity value is 900 multiply with natural log of the final temperature of the aluminum. I have to take this value. This is common for both water and aluminum. So 343.6 divided with 373 Kelvin, which is equal to 100 degrees Celsius, which is the initial temperature of the aluminum. Now I'm going to multiply all these. Let's see what is the answer for this entropy change for the aluminum. 0.4 multiply with 900 multiply natural log of 343.6 divided with 373. Here I got the answer as minus 29.56, and the unit for the entropy is joules per Kelvin. So this is the entropy change for aluminum, which is the answer for the second question, part B, right? So this is the answer. In the similar way, I'm going to find the entropy change for water. So we are going to do the same type of method for calculating the entropy change for the water, which is our C part 3 question, which is the third part of the question. So we are going to find the entropy change for water. I'm going to use the same rule, integration of m of water, that is mass of the water, the specific heat capacity of the water, and dt over T. And here we have to use the initial temperature of the water and the final temperature of the water. So the final temperature of the water is common for both aluminum and water, which is 343.6 Kelvin. But what is the initial temperature of the water? Which is 20 degrees Celsius. When you add 273, we will get the answer for 293 Kelvin as the initial temperature of the water. So now we will take the constant term mass and the specific heat capacity value outside. So mass of the water, specific heat capacity of the water, integration, the lower limit T initial of water, T final of water, and dt over T. And here the natural log integration of dt over T will give natural log of T, right? So here mw cw and natural log of T. So when you apply the initial upper limit and the lower limit, you will get T final of water divided with T initial of water. Now I am going to substitute the value here. The mass of the water is 50 grams. In terms of kilogram, this is 0.05 multiply with the specific capacity of the water is 4187 multiply with the natural log of the final temperature of the water is 343.6 and the initial temperature is 293. So I'm going to calculate these values for getting the answer for the entropy change. So 0.05 multiply 4187 multiply natural log of 343.6 over 293. I got the answer as 33.35. 33.35, and the unit for the entropy is joules per Kelvin. So this is the answer for the entropy change for the water, which is our third question, part C, right? Now in part D, which is our fourth question, we are going to find the entropy change for the entire system. Which system? The aluminum as well as the water. So for part D, we are going to find the entropy for the whole system. What is the meaning for whole system? The whole system means aluminum and water together. So we have to add these two answers. The entropy change for the whole system, which is equal to the entropy change for the aluminum plus the entropy change for the water. As we already calculated the value for the entropy change for the aluminum, which is minus 29.56, I have to write this value for aluminum minus 29.56. I have to see one more time, minus 29.56, yes, right, plus the entropy change for the water is 33.35. So let's see what is the entropy value for the whole system. So 33.35 minus 29.56, we got the answer as 3.79. 3.79, and the unit is joules per Kelvin, which is the entropy change for the whole system. W stands for whole, S stands for system. So this is the answer. The most important thing, your entropy change always gives the positive value. But sometimes when you calculate the entropy change for only one system, sometimes you may get negative value. But when you just go for finding the entropy for the whole system, what is the whole system here? You have to find the entropy for the whole system is aluminum with water. But you have to see here, we will get the positive value because the entropy change always increases. That's the reason here we got the positive value. You will never get negative value for the whole system. Clear? So this is the answer for the last question. That's it. Thank you.